Hello everyone! Good morning, good evening, good afternoon, or whatever time you're watching this. Greetings to all of you, and welcome to another episode of
Come and watch, learn new things about everything around you in just one stop. Here at Math, we explain it all. We solve it. Difficult problems you don't understand, teach it all. Make it easy for everyone. It's all at Math. Here at Math. Here at Math. We explain it all for you.
Have you ever noticed that sounds change their pitch when traveling past you? Let's say you're standing at a stoplight, minding your own business, when all of a sudden, you hear an ambulance.
The siren wails a high pitch from half a mile down the road. You see the approaching vehicle and wait patiently while the ambulance speeds through the intersection. Once it passes, you notice the siren sounds deeper. It has a lower pitch than it did before.
Why did the sound of the siren change? This common occurrence happens in something we call the Doppler effect. The Doppler effect isn't just about ambulance sirens. It's an important phenomenon that occurs in all types of waves. Sound waves, light waves, and even water waves.
Scientists have used the Doppler effect to make some amazing discoveries. Let's learn a little more about this phenomenon, so we can see why it's so important. Doppler effect refers to the change in wave frequency during the relative motion between a wave source and its observer. It was discovered by Christian Johann Doppler, who described it as the process of increase or decrease of the starlight that depends on the relative movement of the star.
Let's say, for example, on a very hot afternoon, you see your classmate running very fast and screaming very loud. Let's assume that the frequency of her voice is 579 Hz at a rate of 3 meters per second because she was being chased by a big angry dog. What frequency will you hear as she approaches you when the speed of sound is 353 meters per second? In this scenario, the Doppler effect is described by the following equation. By substituting the values into the formulas, we will end up with
Performing the operations, we will get 583.96 Hz of apparent frequency. As we have observed, the apparent frequency is higher than the actual frequency since the source is going towards the observer. Let's try this again. Now with your classmate already past you. This time, instead of using negative sign or subtraction, we will instead use a positive sign or addition since we are expecting a lower value for the apparent frequency, since the source is already past the observer. Therefore, the numerator must have a higher value. Doing the operations again, we will get the value 574.12 Hz, which is lower than the actual frequency as stated earlier.
Now we hope we've learned something new today. That's what we do here. Am I right? No.